Thank you for that introduction. And in fact, what Lars doesn't know is that all I learned about stars was in fact from Stars with Lars, which was the class that he taught my advisor at the at UC Berkeley. And you know, there are many renowned faculty at big research institutions, but as you may know, they're not always hired for their teaching prowess. Lars, however, was an excellent teacher. So my stars class in graduate school was not as epic as his. And so when I went to my advisor saying, oh, I'm learning anything, he handed me this beautiful set of notes. And on the outside, it just said, Stars with Lars. And it was many years before I got to meet the infamous person. But so anything I say about stars, you should really thank him.
Or blame him.
Or blame him. Yeah, if you don't like it, it's all his fault. That's also true. All right, so tonight I want to talk about this question, you know, is there a Tatooine? This is one of those cases where I think Hollywood was in fact more creative than the astronomers, because they posited that there could be life around a double star system back in the 1970s, and then it took us another 35 years or so to discover that these systems actually existed. And so what I want to do today is sort of walk you through that by starting with a review of what I'd call the observational exoplanet revolution. Now, I know that this is a theoretical physics institute, and what I do is very theoretical, but I have to be honest and say that in the field of exoplanet research, we have been driven by the observers. They keep showing us that all these things that we never dreamed of do in fact exist. And so that's what makes it such an exciting field to work in, because we're constantly, you know, sent to think about new things that we had never pondered before. Now, what I'll show you is how these gravitational interactions that we're going to study in these exoplanet systems actually date back to the 18th and even the 17th century. So this is a portrait of Pierre-Simon Laplace, and for those of you who have studied math or physics, which I imagine is most of the room, I'm sure his name is familiar. It's plastered over all sorts of equations and things like that, and so many of the basic underlying physical problems, or what we often call celestial mechanics, which is basically the theory of orbits, derives from things that were first discussed in the 1800s. And I'll show how we can use this sort of classical part of physics to probe the mysteries of both planet formation and even star formation. And while I am no GR expert, I will mention LIGO in this talk. So. No, but I'm going to really mention LIGO. All right. And following on that, please do interrupt me, because I have heard myself talk more than all of you and more than I want to ever hear. So just interrupt me and stop me. If you want to hear something else, we can get sidetracked. That's what I love about talking to groups like this. Okay. So pre-1995, this was our view of planets. We had our solar system. We had 8 shining examples that showed great diversity of the type of planets. We have these small rocky bodies that are close to their parent star, and then we have these gas giants and ice giants that orbit further away. And these are not spaced to scale, but their sizes are to scale. And we spent many years as theorists coming up with great theories that explained just why the system was configured in this fashion. And then the Kepler Space Telescope came along and changed everything. Now, the Kepler Space Telescope was not the first mission to discover exoplanets, but this is really where the revolution happened, where we went from knowing about tens of planets outside of our own solar system to literally thousands. And in some ways, as a technical mission, Kepler is extremely boring. It's this amazing spacecraft, you launch it into space, you point it at one patch of sky, and then you just stare at it for 4 years, and you never move. Now, that doesn't sound exciting. But the reason to do that is because the way that Kepler is detecting exoplanets is by looking for transits. And this is basically just an eclipse. So how many people have seen this solar eclipse or lunar eclipse? How many people are going to see the total solar eclipse? What? Do you not know that there's going to be a total solar eclipse in the United States on August 21st? If you don't have plans, make them. Now, it's not very far from here. You should do it before the plane flights and the car rentals are all booked up. Just drive a little bit north or east. You can go east, too, if you prefer. Anyways, it's going to be phenomenal. Okay. Anyways, transits are eclipses, which means you have a star, and you are staring at a whole bunch of stars for a long time, And suddenly, a planet crosses in front of the disk of the star, and it blocks a little bit of the light and creates this dip. And so what Kepler has done is stared at 100,000 stars and just watched for this to happen over and over and over again. And the way we identify these as actual evidence of a planet and not some other random blip in our data is we look for a periodic signal. So it comes by once. Well, okay, who knows what that could be? It comes by twice. That's starting to get interesting. But what we really need is for it to come by 3 times, and for the timing between the first 2 dips and the second 2 dips to be the same. Because that's a signature of the periodic orbit of a planet. It takes the same time to go around the star every single time. And now this method, where we look for these dips, requires a very special alignment between the star that we're looking at and the planetary system. It has to be that when the planet comes across, it crosses right in front of this disk. But you could have a system where the planet was orbiting like this, and we would never see it. And so that's, in fact, the majority of the systems that we're looking at. We're not seeing the planets that are in them. But because it's a simple geometric effect, I can tell you, for every planet that goes across like this, there's so many planets that would go around like this, assuming that the distributions are just random. Right? There's no reason the planets should know that we're sitting here looking at them. There's not that many aliens. There's probably some aliens, but they didn't get to choose how their planets orbited the star. So anyways, this is, despite that, we've been able to discover a phenomenal number of planets. And so what I want to show you now is a really beautiful illustration of this. And this is a movie put together by a colleague, Alex Parker, who's at the Southwest Research Institute. And this movie actually has won some awards, been shown at film festivals. But what you'll see here is sort of a compilation of all of the planets that were discovered as of 2012, which is really when the bulk of the Kepler mission ended. And you're going to see them imagined as if they were all around one star. Now, we've observed these around many, many stars. Probably over 500 stars have planets. But we're going to look at them all as though they're orbiting one star so you can get a sense of the range. And the sound is not working. Oh, you're stuck listening to me. It was a nice 9 Inch Nails soundtrack, but okay. No, it's quite soothing. You can go look it up afterwards. So what you're seeing here is we're actually zoomed in onto the disk of the star. And we're now going to zoom out. And each of these black disks here is a planet with the correct size and orbital period as discovered in the Kepler data set. Now again, they're not all orbiting the same star, but this is just to give you a sense of the diversity of the type of systems that we've seen. And you can see that one side is illuminated as they are facing the sun, and the other side is dark, just like we see phases of planets in our own solar system. And what you're seeing now is we're zooming out very, very slowly, and soon you will be able to see orbits for reference of planets in our own solar system. But the thing I'd like to point out, here we go, coming out, coming out. So this is Mercury's orbit. So all of these planets that we've discovered are on very, very close orbits to their host star. And that's because of the way that we found them, not because most planets are intrinsically really close, but we're looking for those periodic dips. And if we're only looking for a few years, it's going to be much easier to find things that are going around once every 20 days instead of every 3 years. And so now you're seeing the image tilt face on, and you can get a sense again of the diversity of these different systems. Some of them are very close, some of them are far. There was a handful that you may have seen going out towards where Earth orbits, again for scale. And in a moment here, it's going to tip back the other way, and you'll notice one other feature, which is related to this selection effect that I mentioned before, where all of the planets are in a very, very thin disk. They're just pancake flat. And that's mostly because that's the only way that we're able to discover them, because we have to see them cross in front of the disk of the star. There's Mercury's orbit again as we zoom out. And you can see some of them are going around on these sort of inclined orbits as well.
Would we consider these moons of that planet?
this is a star. These are all planets.
They're all planets.
Yeah. So this is, and again, all the planets aren't really around the one star. We're just imagining what it would look like if they were all orbiting the same star. But you can see they have a variety of different sizes. They cover a wide range of periods.
Are most of the orbits counterclockwise?
We don't know, actually, because what we see is just the light dimming, and we can't necessarily tell from most systems which direction it's coming from. These are, again, all put around the same star in the same orbital configuration for reference. And there we go again. And here's Earth way out here. So again, you can see the types of systems that we're discovering are very, very different from our own. And this has really thrown much of our sort of classical theories of planet formation into a whirl. And so what I want to talk about is, that's a nice movie, but how do we actually extract meaning from all of this data? Right? We have all of these detections, all of these discoveries. How are we going to learn something? And so we have this very simple picture of how a planet might form, where you start from this big diffuse cloud of gas and dust that collapses under the force of gravity to form the nuclear engine that is a star at the center. And this material drains the star over hundreds of thousands of years and ultimately leaves behind this disk in which planets are forming. But this classic picture doesn't really tell us the whole story, and there's so much uncertainty that we still have. It's a really active area of research. And one of the things that I find so interesting about this area is that you don't just have to be a physicist to understand what's going on. If you really want to put together the whole picture, you need to understand chemistry. You need to understand how little tiny dust grains grow into giant planets and Jupiters. And so there's so much physics that goes into it. And so what I wanted to do today is take a step back and simplify a little bit and say, okay, there's all of this physics that we might need to worry about if we want to understand that whole process. But there's one thing we understand really well, and that's gravity. So what I want to talk about now is what we can learn about all these systems if we really just focus on the gravitational effects. And that's how we get back to Laplace and the classic mathematicians of the 17th
Can I ask, are you able to tell from Kepler whether a star has multiple planets?
Yes, we have discovered many systems that have multiple planets, as many as 6 or 7 in some systems. And in fact, it seems that a large number of planets are in multi-planet systems. And I'll show you a few examples in a little bit. But before we get to that, I'm gonna spend a little bit of time going back to very, very basic physics, because this is really where it all starts, and that's the two-body problem. And this is how you understand how two bodies that are interacting through their own mutual gravitational effects orbit one another. And it's one of the simplest problems that we can look at in physics, and it has an analytic solution. If you tell me today a body has this amount of mass and its partner has this amount of mass, and you tell me where it is in space and how fast it's moving, I can tell you what it's going to do for the rest of eternity. Very, very simple. It's basically, you put it on an orbit like this, it's just going to keep doing that. Now, there's other physics that you might worry about, but we're not going to go there. Lars spends all his time worrying about tides and complicated interactions like that, but we're just talking about gravity today. That's the easy stuff. And, there's very simple things that you can understand about it. So, for example, the stars orbit their common center of mass, which is why the big star is making this little circle and the smaller star is making this larger circle. This is like balancing on a seesaw. So if you put me at one end and any normal person on the other, the normal person has to be much closer so that they don't fling me into the air. So this is great. We understand this extremely well. Like I said, I can write down the answer and tell you what will happen for all time. There's one more case where I can start to make progress just by writing down very simple equations, and that's the so-called restricted three-body problem. And the restricted in this case means I have two things, they both have mass, and then I can tell you what a little tiny blip, an imaginary test particle, is doing as it reacts to the gravity of those two bodies. So that's what restricted means. And it's a very, very limited case. It means I can think about two things that are big and one thing that's really tiny. And the classic example of this in celestial mechanics was, say, the sun, Jupiter, and a comet. And like this problem of two bodies, where I can write down some things analytically, I can just write down an equation and tell you the answer, we can make some progress when we make this approximation. And If you want to see the gory details of it, here you go. These are the very nice, simple set of equations that we can solve. I won't go through them in too much detail, but it's basically saying if I tell you where something is, say x, and I tell you how fast it's moving, that's a derivative of, say, y dot. I can tell you about the accelerations based on their positions in space. And the magical thing about this particular problem is that there's a conserved quantity. And all of you physicists in the room know that that's like the gold standard, right? If you have a conserved quantity in your problem. So in the restricted three-body problem, we still have something that's conserved, and that lets us say something about where orbits can exist. So in these two illustrations here, for example, if I have these two stars, for a given planet, I can tell you, well, in this case, it can move anywhere in this white space, but in this case, it's trapped around one of the systems. And so this is a way that we can begin to make progress. And so now let me move beyond the equations and tell you how we apply this. So I showed you an image of all of these beautiful planets orbiting a single star that Kepler has discovered. But in fact, many stars are not like our sun. They are not on their own. They have a partner. And sometimes they have two partners. In fact, sometimes they have three or even four. And they are orbiting each other periodically in time. And if we look out into our galaxy, as many as half or more of the stars that we see are doing this orbital dance. And what Kepler has shown us is that we not only have these stars orbiting each other, but we can have planets in these systems. And this is a great way that we can apply that classical problem of two big things and one little thing to new discoveries. Because planets and binaries have this same feature where two things are big and one thing is small. And what we can see is that you can get sort of these two flavors of systems. You can have one type where the planet just goes around one of the stars. So you can imagine this is just like, say, the sun, the Earth, and a moon, except everything is scaled up. Both things are stars, and then you have a planet. Or, for the Star Wars fans in the room, the sexier kind is, of course, the one where you have the two stars in the center, and you have one star going around both of them, the so-called Tatooines. And we can apply these same basic lessons from the three-body problem to say something about, say, where the planets can exist. So if I take that first case where I have the planet going around one star and then that whole system is orbiting with another star, I can say that if I put the planet really close and I put the star kind of far away, this is okay. This is a stable configuration. If I put the planet too far away from one of the stars, it starts getting gravitationally tugged a whole bunch by the other star, and so this can't exist. It's a very unstable configuration. Same thing goes in the other case. If I take two stars and I put them really close together, and I put a planet going around that's far away, we're in good shape. That's fine. That'll keep going forever. But if I have this case where the stars are kind of far apart and the planet is too close, that's not going to work. That's unstable. And in fact, yes?
So unstable means it's going to ultimately decay and
yes, something bad is going to happen. And I'm going to show you ways in which bad things can happen in just one moment.
Thank you.
Okay. So this is the basic picture. This is bad. And I should point out that this problem of things kicking each other too much and becoming unstable doesn't just exist in binary systems. It exists in single star systems. And so if you take planets and you either make them too big or you push them too close together, they will also kick each other and drive themselves unstable. And you can think of this very simply. The gravity from the central star is really, really strong. And so mostly the planets just want to go around because they feel the gravity from the central object. But if you keep adding in other massive things, they can start to kick and tug and pull. And if you make them too big or too close, then those other gravitational tugs get really strong and they drive all the orbits unstable. So, what does this look like? Okay, keep your eyes on the balls. We've got system 1 on the left, system 2 on the right. We're starting out with blue on the inside and green is on the outside. You might have to have your neighbor watch one side and you watch the other. But you can see these are almost the same. I've spaced one planet by the Earth-Sun distance and one just a little bit further out. Oh, I missed it. Yeah. Okay, right? Uh-oh. So that was bad. So this is an example of a chaotic system where you see these two orbits, they switched places. And you keep watching it, right? These guys are going around in nice circles, whereas these ones, the sort of shape of the orbit was changing in time. And this is a case where things got a little messy. They were too close, no fun. So that was a single star with 2 planets. Let's look at what happens when we have a binary with planets. So now I've put these guys just a little too close. And you can see what happens, right? Now the gravitational tug from this other star in the system is too big, and instead of the planets just continually going around on nice orbits, they start to do a little dance and go back and forth.
The weather must be interesting.
So at the end of the day, there's probably not anyone to look around and see the weather, because I'm showing you a pretty special time in this system. If we wait a little bit longer, what's going to happen is most of these are going to crash into this star, crash into this star, or are ejected off into outer space. They just don't survive very long. Maybe tens of thousands of orbital periods before they all get lost in one way or another. And so I hope this illustrates to you an example. Sort of, we can already start to make some comments on what kind of systems we should expect to be out there. And this is all using these very, very simple arguments based on where planets can exist and where they can't, just based on the gravitational interactions between them. Yes?
These planetary motions all with lightweight, marble weight test planets?
Exactly. These are in fact all test particles, and if they weren't, you would see them bumping into each other and causing the whole system to fly apart. So these little red guys aren't interacting with each other. They don't feel the gravitational tug. They only feel the gravitational tug of the blue star and the green star. All right. Any other questions before I move on from the tadpole movie? Okay. All right. So great. I've shown you that there's some basic gravity, but really, other than maybe caring about Star Wars, why is this interesting? Why should we specifically try to understand planets that live in these binary systems? Now, it turns out that they're not as common as the planets around single stars. When we take all the statistics we have from Kepler, it tells us that there are potentially more planets in our galaxy than stars. And there are billions of stars in our galaxy. There are probably more planets than that. Now, that doesn't mean that every single star has its own planet, because some are rich and some are poor, some have many, some have none. But they're very, very common. They're a little less common around binaries, but the reason that I think it's so interesting to study planets around binaries is because it doesn't just tell us about planets and our own solar system, it tells us about star formation. And I'm going to try to convince you now that that's potentially a more exciting problem from a broad perspective of theoretical physics than just the measly planets. So here's why. Planets in binaries are like a ticking clock, because there's a couple things we know. We look at stars that are young and are making planets, and we know how long it takes. We know that the planets have to be made in a couple million years. Now, maybe that sounds long to you. For astronomers, that's a blink of an eye. That's super, super fast. And the fact that we know that little time scale tells us that when we see a planet orbiting 2 stars, the 2 stars had to get into that configuration in a million years. And it turns out that that rules out many, many theories of how binary stars form, of how they come together. And so by ruling out many, many theories of binary formation, we can actually make progress on a whole wide range of astrophysics. And this image here on the right, this was taken with a sub-millimeter telescope called the Atacama Large Millimeter Array, which is in the Atacama Desert in Chile. And if you've looked at a lot of these images, you would know that this is spectacular. And what we're looking at here is actually a forming binary star system with a third body that's in this large spiral, because the whole thing is undergoing these strong gravitational interactions. And this is particularly exciting to me because this discovery was very, very recent. But it's a problem I've been studying for over 10 years. And in fact, there's a really nice KITP connection here, because these simulations, which I started running back in 2007 at a KITP workshop, predicted that we would find these forming binary star systems. So the last time I was here is when this endeavor started, and then 10 years later, we sort of found the observational evidence. Okay, but
About how far away is that system?
this system is about 100 parsecs away, which is 100 light years. So it's pretty close, which is why we get these phenomenal images. But okay, so maybe I've convinced you that we can learn something about the formation of binary stars, but I haven't told you why. But the reason why is that binaries are really the most fundamental thing we have in all of astrophysics. So maybe all of you have your pet, thing in astrophysics that you think is the most exciting, and binaries cover them all. Do you like gravitational waves or general relativity? Well, the way that we confirmed the theory of general relativity was by seeing the decay of the orbit of two pulsars in time. If you don't like GR, maybe you like dark energy. Do you know how we learn about dark energy? It's through this special type of stellar explosion called a type 1a supernova. Do you know where type 1a supernova come from?
Binary star system.
Binary stars, exactly. Do you like black holes?
Yes.
Okay. How do we know about black holes? We know about at least stellar mass black holes when they are orbited by another star in a binary system. Otherwise, they're invisible and you can't see them. You must like gravitational waves, right? You like gravitational waves. Those also come from binaries. If you like planets, now I've talked about planets in binary systems, but the only way we can do anything with all of the discoveries that come from Kepler is because we have binary stars, which allow us to couple our models of the theoretical physics of stars, nuclear fusion, and all of that chemistry with their temperatures and their luminosities and their sizes and their masses. We need stars in binary systems so we can make all of those different observations and combine them together and test our theories. When we detect planets around stars, the only way I can tell you that what I'm looking at is an Earth-sized planet versus a Jupiter-sized planet is if I know how big the star is. Otherwise, I'm totally lost. If you're interested in basic cosmology, it turns out that the reionization of the universe, when the universe transitioned from being neutral to mostly ionized after the first stars and galaxies were born, it turns out that binary stars may have been important for that too. And now maybe you think I'm biased because I really like binaries, but I would say I'm not biased because 2 Nobel Prizes have been awarded for these discoveries, which are fundamentally about binary stars. And these are Nobel Prizes in physics, not astrophysics. And I would argue that probably we're going to see another one coming in the next year or two. So we've got 3 Nobel Prizes for the field of binaries. So clearly this is the most important thing in all of astrophysics. But if you're not sold on learning about all the rest of astrophysics, maybe you just like planets. Maybe you just want to know where Earth came from. And that's a reasonable thing to say. And I would argue that these systems are very, very helpful for our understanding of where things like Earth came from. And the reason is that planets and binaries tell us about the extremes of the physics, right? I can have some model and I say, let me take a star like a sun and I'll put down some dust and gas around it, and then I'm going to tell a story about how all that stuff turned into an Earth. What I can then do is say, well, okay, I have a nice story that you told about what would happen around the sun. Now I'll throw a binary into the mix. If I have some system that I've discovered where I've got an Earth-sized planet and another star sitting over here, you've got to take that theory and make sure it works in this system, or else it's garbage, right? You can't have a theory that only works in like a tiny fraction of systems. I mean, this is kind of Occam's razor. Maybe you have a different way of making planets in every kind of system, but I find that very, very unappetizing. And so if we take these special systems, they can falsify many of our models. And this is just one kind of neat example that I'm showing here, where this is actually a triple star system that we discovered just this past year, where you've got these 2 guys over here. These 2 little stars are on a tight orbit around each other. It's orbiting a 3rd star on a really wide orbit, maybe 300 times the distance between our Earth and the sun. And then there's this funny planet sitting in between, a little bit, outside of the orbit of Pluto. I don't know what it's doing there. I don't know how it got there. And this system just broke a whole bunch of the models that we have for how planets form. And so it's great. I mean, it keeps me employed, right? Like, they keep breaking our models. So now we have to go back to the drawing board and say, okay, well, this exists, so that rules a few things out. We also have some more mundane reasons maybe for liking the planets in binary systems. And so this is one called Kepler 47. This was one of the first systems that was discovered around a binary with Kepler. And it's a stable Tatooine-type system. So you've got 2 stars, and then there are 3 planets that are on these nice, stable, circular orbits, almost circular orbits, going around the 2 stars. And
Question?
Yeah.
If you were looking at the dimming for this, it's much more complicated, of course. How do you even...
That's a great question.
The brightness is going up and down just because of the stars.
Right, so this is finding these systems is kind of a huge challenge because you have 2 things going on. So the stars themselves, that's a bad color, right? The stars themselves are orbiting each other. And so if you look at the brightness as a function of time, you'll see these big dips. Like that. Okay, so that's the 2 stars. The planets, right? And then I've got these little guys that are going around as well. And now there's 2 problems. One, the planets are going to be a tiny little signal by comparison. So now you've got to find that. But what makes matters even worse is that the stars are a moving target. And so you don't get that nice, clean, periodic signal that you got with the single stars. So maybe the first time the planet comes around, right? Let's say the stars are in this position, the planet comes by, and it crosses in front of this guy, but it misses this one. The next time, the stars are in that configuration, and so when it comes by and blocks out the light from this, it's not exactly 1 period away, it's some other value. And so all of the systems that look like this, they were discovered by people going through the data by eye. There's no computer program that could do this. Yes?
Isn't there a problem with those 2 stars merging?
No, they are far enough apart that the tidal interactions are actually not that strong. You're right that it's very hard to tell with this scale, and the sizes of those yellow stars are not equivalent to the stellar radii. But you're right that understanding how the stars got into their current configuration, then we do have to worry about the stuff that Lars thinks about a lot, which are these tidal interactions. Okay, so maybe you don't think it's boring that they're just going around in circles, but if you did, what I would tell you is that the other thing that's super cool about circumbinary planets is that we often find them in the habitable zone. And the habitable zone is defined as the distance away from the stars where the temperature of the planets is expected to be about right to have liquid water. Now, that doesn't mean that they're habitable. That doesn't mean that there's life. It doesn't even really mean that there could be liquid water. And in fact, for this particular system, even though they orbit, you can see sort of in between where Earth and Venus are, they're not solid terrestrial planets. They're gas giants. You couldn't go land and stand on them. So, I mean, maybe you could have bacteria in their atmosphere. I don't know. But you're not going to find Luke Skywalker. And in fact, all of the circumbinary planets that we've discovered so far are more of that sort of massive gas giant type as opposed to the tiny Earth-like systems. But in fact, I told you that this was a problem, the fact that it's really hard to find them. But it's also a bonus because the fact that the stars are far apart actually makes it easier for us to find things that are far enough away that the temperature could be cool enough to find habitable planets. Now, I'm going to take a little bit of a sidetrack here, and I have to talk about one of my other favorite astronomical objects because it's very closely related, and that is Pluto. Now, many people were very, very sad when Pluto stopped being a planet. But that is such a mundane existence because Pluto is so much cooler than a planet because, in fact, it's a little tiny microcosm of a circumbinary planetary system. Because Pluto has this moon, Charon. But moon is a terrible word to describe Charon. It's 1/10 of the mass of Pluto. Our moon is relatively big in the solar system, and it's 100th of the mass of Earth. So this thing looks like a binary star, and it has 4 tiny little moons, in my model planets, that are going around it. And so we can use circumbinary planets to learn about planet formation sort of in the rest of the galaxy, but we can use the Pluto-Charon system to say something about the formation of planets in our own solar system. And this topic has been very, very exciting recently because I'm sure you all saw that New Horizons, which was launched a decade ago, finally had its flyby and took some phenomenal pictures of this system. So it was launched back in 2006, flew out, interacted with Jupiter, and then was sent out to have an encounter with the Pluto system. And in fact, it's currently on its way out to explore the Kuiper belt, the sort of debris left over from the planet formation process in our own solar system. And it had an amazing trajectory in space. So this is the line that the spacecraft took. This is Pluto, this is Charon's orbit, and this is the innermost moon in the system called Styx. And it threaded the needle and went right in between. And in fact, the guys who were planning this mission, they had a really hard job because they had taken these images with the Hubble Space Telescope, right, to find these little moons here. But what they weren't sure of was whether or not there was anything else tiny in the solar system. And so they kept looking and looking and looking to see, do we see any rocks that we're going to run into? Do we see any rocks that we're going to run into? And they had all of these crazy tests where they'd stay up for 3 days straight and be like, okay, suppose we found a rock, let's recalculate all the orbits so we don't run into it and crash the space telescope. But they didn't find anything. And what they got with these were these phenomenal images. So this is Pluto, this is Charon. These are nominally false color images, which means we've combined wavelengths that are somewhat outside of the optical where your eyes can see to sort of make something that's more visually appealing. But nevertheless, you can see that there's all of this amazing substructure. And I mean, we could talk for hours about all of the things we're learning about planet formation just by seeing these two bodies. But I'm not going to talk about that today. I'm going to talk about, again, going back to gravity and what we can learn from the orbits of the little moons that are going around this amazing local circumbinary system. So, just like I talked about before, we can say something about the properties of the system based on the stability, right? We have Pluto-Charon, they're going around on a nice circular orbit. And then we have all of these little moons that are interacting and tugging each other gravitationally. And we know for a variety of reasons that this system is ancient, that it probably formed very early in the solar system, billions of years ago. So if I construct a model where those gravitational tugs make the system fly apart in 100 million years, that's not right. Something's got to be wrong. And what's really cool is that we can say something about the masses of these little guys, and therefore their composition, what they're made out of. And this is something that we don't often think about in astronomy, but in many ways, looking at stars is a lot simpler than looking at rocks. And these are all basically just tiny little rocks floating out in outer space. When we look at a star, it's shining, right? It's emitting light. And we have all these very clean theories that say, okay, how much mass is in the star? How dense is it squishing things in the core of the star? How much energy is being produced by nuclear fusion? And then I know how much it's shining. That's, relatively speaking, pretty simple. But if I'm looking at a rock, it's very hard to know if I'm looking at a dark rock or a snowball, because there's an uncertainty. All we're seeing when we look at these pretty pictures is just some amount of light. And the amount of light that we see depends on how much the starlight is shining on it and how much is being reflected back into our eyeballs. And this property of how much light it reflects back is called its albedo, its shininess. And so you can imagine I could have a really big, heavy, massive, dark thing, or a really dense, somewhat less massive dark rock, or I could have a giant, fluffy snowball, or a smaller, kind of fluffy snowball. And depending on how much light they're all reflecting, I could be looking at very, very different objects. And so what we observe is how much light we're getting. If I want to say something about what it's made of, I need to know how heavy it is. And so we can actually tell by requiring that these orbits remain stable for the lifetime of the solar system, that they don't kick each other around too much, we can tell how big these little rocks are, and then we can say how massive they are, and therefore what they're made of. And so one of the things that came out of this kind of modeling was that the moons of Pluto and Charon are icy. And we were able to predict this long before, at least 5 years before, New Horizons got there and checked and found that it was right. So we were able to validate our models. So this is another example of where these very, very, finely tuned dynamical systems can provide amazing insight. And now that we know what those little rocks are made of, we can say something about how the system arose, how it formed. We can say something about the collision that produced it. We can say something about the types of objects that were the building blocks of planets in the outer reaches of our own solar system. And because we were able to validate this one system, it means that now we can have the confidence that if we can make these models for other systems, even if we don't have billions of dollars to send a spacecraft to go visit it, maybe we can learn something about what we're looking at. So I'll show you one more system.
Could I just ask on that count?
Yes.
It looks as if you're more uncertain about Pluto than the other things, but you've got a big range there.
Yeah, so these are good. Yeah, so these are examples of the albedos of things you might be familiar with: asphalt, sand, snow, Enceladus. The reason that these have big error bars, is because they don't actually have one reflectivity. Before New Horizons got there and took these amazing images, what we saw was that the brightness of the object changed as it orbited. And that is where some of that range came from. Now we know why. It's because the surface of Pluto especially, and to some extent Charon, has these very, very detailed features. So there's this, vast glacial moraine. Now it's probably not water ice, it might be nitrogen or something like that, but that's on one side, and this is going to be much shinier than this dark red rocky region over here. So it's variability, not uncertainty. All right, so I'm going to show you one more of my favorite systems that we found that is telling us something about how planets form. And that's the system called Kepler 444. It is 5 sub-Earth radius planets that are orbiting one star, and they're all packed within 0.2 AU, so 0.2 times the Earth-Sun distance. So these things have periods of basically 4, 6, 8, 12 days. So they're very, very short period, like the ones you saw in that Kepler movie at the beginning. This whole system is embedded within another one of these triple star systems where these guys, they're orbiting each other maybe once every half a year. And this whole system is orbiting around the planetary system once every 80 years. And now this is not to scale, but I have drawn this orbit to be really elliptical, really stretched out and eccentric, because it is. If you know anything about Keplerian orbits, this has an eccentricity of 0.86. The maximum value is 1. So it's really, really up there. And this system basically passes within Jupiter's distance of the other planetary system. And so this is another one of these examples where we can now test all of our models of planet formation that we use in our own solar system. And one of the really peculiar things about this system is that we think that the disk around which, in which all of these 5 tiny little planets formed was probably only out to about, the distance of Mars, because the gravitational kicks from that other pair of stars coming around would have ripped the rest of the disk to shreds. So for the last 5 years, we've had so many great models of planet formation, and they told a story about how we took this nice icy material from far away from the star, because, if you take 2 snowballs and you throw them together, maybe they'll stick, but if you take 2 rocks and you try to throw them together, that's, from personal experience, that does not work, right? You can't grow rocks by throwing them at each other. Maybe you can grow snowballs by throwing them at each other. So there was this great story about how we were going to fix all of the problems with planet formation by sticking snowballs together instead of rocks together. Well, Nope. Throw it out the window. We made 5 planets, and there is no snow in this system. So now we have to go back to the drawing board and say, okay, maybe sometimes you need snow, but certainly we can do it if we only have rocks. And so this pushes us towards considering new instabilities between the dust and the gas and the disk that might allow things to clump together without relying basically on electrostatic forces. So I'll just conclude on the Star Wars theme by putting up 2 quotes which I think really characterize our pursuit in this field. One, much to learn you still have, my old Padawan. This is just the beginning. And in the spirit of you coming here and giving me your evening, please always pass on what you have learned. So thank you very much for your attention.
One of your earlier slides showed massive gas giants within a very short.
Yes.
How is it that in our solar system the gas giants are further out than the rocky planets?
It's a great question.
No answer?
Well, okay, I'll give you a couple answers. So one answer is sort of the anthropic principle, which is that we think in systems where a Jupiter-mass planet managed to get all the way in close to the star, it would destroy terrestrial planets like our own. And so the fact that we have these rocky planets that still exist is because a gas giant didn't sweep its way in. And if a gas giant had swept its way in, it would have knocked everybody else out. There's still a lot of competing theories, though, for exactly how those big things arise very close to their host stars. Some of them require this motion inwards, like they formed very far out, maybe where our own Jupiter is, and then got swept in. But there are some models where they form sort of interior to where our own Earth is, and that's something we're still working on.
Ron? You have this planetary or stellar accretion disk, and it's rotating, and I suspect that you're discriminating between rocks and gas, and the rocks go out and the gas goes in because it's not as dense. Why do you form binary or multiple stellar systems if it's all rotating? Is that turbulent? Is that gas turbulence? Or what creates?
This is not a setup, so I put in one more movie just for fun. It's really not a setup. So this is a movie of a
Pay me later.
a simulation of actually the onset of binary star formation. So this is a turbulent cloud of gas, and these red points are stars that are forming by themselves, and the yellow points are binary star systems. So what we think happens is that in many cases there's some net turbulence in the background cloud that either generates a binary very early on, or that there's enough mass at the very, very early stages of when that disk formed to create a binary, and then the disk around it will go on to make the planets. And in fact, it's not the case that the gas goes in and the dust stays out necessarily. This is one of the big problems with planet formation, is that if you take dust and you try to make it orbit around the star, it'll interact with the gas in such a way that makes the dust fall into the star faster than the gas, which is a huge problem if you want your dust to turn into planets, and that's still unsolved.
Where does the turbulence come from in the first place?
We think it's a combination of sort of large-scale galactic tides and supernova and massive stellar winds, but it's actually an open question, sort of what is the dominant force of turbulence in these systems.
What's the origin of the word Tatooine and a specific definition?
You'll have to ask George Lucas.
Oh, okay. It's
just yes.
In your movie at the beginning,
Yes.
you showed Kepler with, I believe, a 4-year life, and you needed 3 observations essentially to. That would imply that shouldn't you have seen more systems with close to 1 year or approaching 1 year?
Right. So there was a handful of systems with 1-year orbits. So there's 2 things. The timing makes it hard, right? Because it's going to be easier to see things that are closer in. There's also the inclination effect, which is that if you have your planet and it's really close to the star, you can tilt it a little bit more with respect to us than if it's far away. So the farther away it goes, it makes it more unlikely. And then there was another problem with the Kepler mission, not a problem with the Kepler mission, it was a problem with our knowledge, where the Kepler folks did these phenomenal calculations of exactly how much precision they needed in their recording of those little dips in the light to see an Earth-like planet at 1 AU. And they did it all based on everything we know about the sun. And we have a lot of data about the sun, and you may know that the sun isn't really constant in brightness. It flickers, right? We have these magnetic field cycles, sunspots, all that stuff. So they took everything we know about the sun, and they did this calculation. And then they turned Kepler on, looked at 100,000 other stars in the sky, and realized that our sun is really pretty quiet and mellow by comparison to all the other stars. So all the other stars are jumping around a whole lot more, so it made it even harder to pick out those little tiny blips that would be Earth-like planets.
Are the multiple planet systems dynamically a chaotic system?
So there are some of them where we can measure that they're interacting because, let me show you this movie again. So, right, we talked about the fact that the orbits are periodic. So this guy comes around once every year or something. And this doesn't have anything to do with the binary. If these planets are close enough together that they're kind of tugging on each other, sometimes they'll tug on each other so that it takes a little bit longer to go around than you would have expected, or a little bit faster to go around than you would have expected. And so we can see that they're interacting. But all the systems that we've observed with Kepler are quite old, probably billions of years old. And so typically we would think if they were really, really unstable, they would have already fallen apart. Now, that doesn't mean they're not chaotic. Formally speaking, anything where you have, more than 3 bodies is probably chaotic. The solar system is chaotic. We just think that it's chaotic on timescales of, billions of years. And in fact, there's been a lot of work to try to understand the fate of the solar system. And if you want to really know how to do the calculation correctly, you would need to know where all the asteroids are. So there's theories that tell you that basically what's going to happen is that Mercury is going to interact with Jupiter and get its orbit excited and maybe crash into Venus. And so all that's possible for the Kepler systems, but they're not like about to fall apart, I would say.
But if they are chaotic systems,
yes,
then the following question probably makes sense. In your calculations of the motion of various planets around there, do you have time retardation in your gravitational forces?
So I don't know why that would matter for the chaos. All of these systems, right, all of these multi-body systems are chaotic in the sense that if I take the initial conditions that I start with in one set of calculations and then I move everything by 3 centimeters, I could in principle get a different answer in a billion years. But that isn't, that has nothing to do with whether I'm calculating the retardation of the forces.
Well, if your force is off a little bit, the trajectory will be off a little bit, which is tantamount to having a different initial condition.
Yeah, sure. But I guess I'm saying there's a whole lot of other effects that are probably more dominant than that, I guess, is what I would say.
Final question, Ron.
Does water form from a supernova explosion or adsorption of hydrogen and oxygen on grains of?
In the protoplanetary disks, it's forming in the latter case. Supernova are, you don't even need a supernova to create the sort of net elements of water, hydrogen and oxygen. You can do that in a much lower mass star just through general nuclear fusion. But we expect that water molecules would be destroyed in the heat of something like a supernova explosion, and then they reform in these colder temperatures.
On granules.
Grains can be one form, but there's a bunch of different, channels to make water.
All right. Kaitlin, thank you so much.